In this video, we will be describing some of the implications of the wave-particle duality nature of matter. As we saw in our recent video, in addition to photons having wave-particle duality, electrons also exhibit both wave and particle-like behavior. An electron's behavioral characteristics can be described either from a particulate perspective, in which we're looking at matter or mass. The particulate nature of matter has to do with its position. We can also look at electrons from an energy perspective, which deals with the wavelength and their frequency. This is exhibiting the wave nature, which we can see through interference patterns. The problem is that we can't observe both properties simultaneously. The more matter exhibits a particulate nature, the less it is exhibiting wave-like behavior, and vice versa. The wave and particle nature of the electron are complementary properties. The more you know about one, the less you know about the other. This level of uncertainty of one or the other properties as you gain a greater understanding of the other was summarized by Heisenberg when he stated his Heisenberg's uncertainty principle. Heisenberg stated that the property of the uncertainties in both position and speed of the particle was inversely proportional to its mass. This can be summarized via the following equation. The delta is meant to signify uncertainty. So delta V is the uncertainty in velocity. Note this is V for velocity, not nu as in frequency. So the uncertainty in the velocity times the mass times the uncertainty in the position, how well we know x, or its location, has to be greater than Planck's constant times pi over 4. This means that the more accurately we know our location, the smaller the uncertainty in the location is, the greater the uncertainty in the velocity will be, and vice versa. So the more you know about the position, the less you know about its speed, or if we think about mass times the velocity, this would be momentum. So the more you know about the position, the less you know about momentum. The position is the particulate nature of matter, and the momentum, or the uncertainty in the speed, is the wave-like behavior. So as you know more about it in terms of the particulate, the less you know about it in terms of the wave, and vice versa. This concept of not being able to determine the exact position and velocity might seem strange, because according to classical physics, particles move in a path determined by the particle's velocity, position, and the force acting on it. This is what we would call determinacy. We have a definite predictable future for all objects. The reason why this would seem more familiar to us is because if you think about the objects that we interact with every day, the mass of those objects is huge, particularly compared to Planck's constant, which is 6.626 times 10 to the negative 34th joules per second. If we look at things down on the quantum level, however, we can't know both the position and the velocity at the same time. So because we cannot know both the position and the velocity of an electron, we can't predict the path it will follow. This is what we would call indeterminacy. It has an indefinite future. We can only predict the probabilities. So the best we can do when we're talking about where an electron is, or how fast it's moving, is talking about probabilities. We can talk about an electron has a high statistical probability of being in a particular region and moving at a particular velocity. So under our classic physics, we would talk about a trajectory, or where a particular particle would move. When we're talking on the quantum side, because particles have both a particle and a wave nature, they have a higher probability of following along the classical trajectory, but they have a non-zero probability of being somewhere else. So when we're talking about the position of electrons and particles down on the atomic scale, because they have sizable wavelengths compared to their own size, we have to talk about probabilities. So a more accurate way for talking about the position of electrons in atoms is in terms of probability distributions as opposed to the atoms following along a set orbit. Atoms following along a set orbit, as in the Bohr model, would follow a classical trajectory. We have a very good idea of where they're going to be located because we know that they are a particular distance and moving in a circle. But via the Heisenberg uncertainty principle, where because particles are exhibiting both a particle nature and a wave nature, and those two behaviors cause uncertainty in the position and the momentum, it is actually impossible to determine with 100% precision both the particle nature and the wave nature at the same time. Instead, we need to refer to it in terms of probabilities. So electrons and other subatomic particles, as well as all other matter, have an indeterminacy to it. This means that the path of an electron cannot be determined from its position and its velocity. The electron energy and position are complementary. The more we know about one, the less we know about the other. For an electron with a given energy, the best we can do is to describe a region in the atom where there is a high probability of finding it. Many of the properties of atoms are related to the energies of the electrons. So we could think about kinetic energy, which is 1/2 the mass times the velocity squared. So if we have a particular uncertainty in the velocity, there's a little bit of uncertainty as to how fast the electrons are moving. In terms of the probability distribution, we will see in subsequent videos that the position of the electron, instead of being described as following along an orbit around the atom, is actually described by what we call a probability distribution. A real-world example of probability distributions would be where a ball is thrown in a game of baseball. There is a higher probability of the ball being thrown towards the center of the strike zone than out in a particular location where it would be considered a ball. So what we would look at in terms of the probability distribution is a high probability of finding the ball on any given throw in the center and a lower probability as we go out per region of space of finding the ball as we move away from the center. We have the same general idea for an electron. There is a particular distance from the center of the atom where we will see a higher number than towards the side. If we're looking at pitches, there is a very high probability of finding a particular pitch near the center, whereas there is a low probability of finding the pitch in somewhere in the ball region or a wild throw coming off way off to the side. So the further away you are from the center, the lower the probability of finding a ball thrown in a particular pitch.